to the final speaker of the session, and the next speaker is Chris Wikle. He is a distinguished professor and chair of statistics at the University of Missouri, and he is going to present the studies that was in his working group, and is about an illustration of model agnostic explainability methods applied to environmental data. Chris, the floor is yours.
Thank you, Monica, and thanks to everyone for attending, and to TIES for making this possible. So I'm going to talk today about the work that some of the work that our TIES working group has been doing, and this is a paper that resulted from this part of the work, and these are the collaborators that helped make this happen. And if there's time at the end, or maybe in the general discussion, I can give some insights to our group. I really appreciated what Matt and Marta talked about with their experiences. This group wouldn't have happened, honestly, without Susan Simmons, who was really made the trains run on time, and her organization was crucial to making this work. So what was our motivation? Well, basically, when Susan asked me if I'd be interested in doing one, I wanted to pick a topic that I didn't know much about, and hope that we could all kind of learn together. And so I had been working with sort of deep neural models for the last few years at the interface of statistics, and I was interested in learning a little bit more about some of the criticisms that statisticians have of these models, which is, one, their inability to do inference, which of the features or inputs are important, and then uncertainty quantification. And so, as most of you probably know, Explainable AI has sort of developed to answer these questions in the last few years, as well as other concerns about deep models such as transparency and fairness. And so we came together to explore these, and back in August of 2021, and don't think I'm speaking out of turn by saying none of us were experts in this area. So the talk I'm going to give today is about the explainability part of this, and we're currently working on a more uncertainty quantification paper as well. So what is model explainability? Well, it basically allows you to check for things like fairness, trying to ensure that predictions are not biased. By bias, in this I mean not so much statistically unbiased as in bias in terms of discrimination against groups that you would not like to discriminate against. Privacy, of course, that's always a big issue with any model. Reliability or robustness, we would like the models to perform well similarly when we perturb inputs, for example. And causality, this is a little bit of a stretch here, but obviously if we can't explain things, then we can't establish causality. So it's part of the link for sure. And then I think trust is super important here. If you're going to use these things to do prediction and they're black boxes or classification, to establish trust, you need to be able to explain why it's making the decisions like it does. And I'd just like to put a plug in for this book, which we didn't know about when we started. In fact, I didn't know about it until we were already had the first draft of our paper written, but it's a wonderful online resource. I think it's the best book on the topic by far. And if you want to learn more about explainability, I highly recommend this. And so a lot of my presentation is sort of motivated by some of the stuff in there. So moving on then, just a little bit about explainability methods, and they're either typically model specific or model agnostic. And an example of a model specific one would be if I had a convolutional neural network and I wanted to describe which features were important by doing a particular approach like layer-wise relevance propagation, for example. That would be very specific to that type of architecture. Whereas a model agnostic method is can be applied to any model, whether it be a black box model or even a parametric model. And I think as a statistician, this interests me a lot more, because I feel like even in models that we typically think we can explain, I think it's sometimes good to interrogate those models with other methods. And so that's what we'll focus in on today. So all we really need is the input and the outputs from any model to be able to do this. And so then the next decision point is whether it be a global or a local method. And of course, a global one's going to describe the whole model, the behavior of the entire model. By that, I mean across all of the inputs and output pairs. And an example of this would be partial dependence plots, which many of you probably have seen in just a context of linear regression. We'll actually use one here and talk about it in a minute, called permutation feature importance. But then there's also local methods, and these are explaining individual prediction instances. And sometimes we could aggregate these, but I think this is something that we don't do as much in statistics, and I think in model building in general, and I think it's a really valuable tool. And so we'll focus a little bit on that as well, and we'll focus on two of those, local surrogate models, Lyme in particular, and then Shapley values. So let me just talk about these things very briefly. Obviously, there's a lot more detail in the paper and then in these other references too, but feature shuffling or permutation feature importance is a global approach that basically it's super simple to think about. It just says, I'm going to look at how the prediction error changes if I permute the feature values. And so that's clearly going to break the relationship between the feature and the true outcome. So if you do that one at a time, then you can measure the importance of that feature by just seeing how much it impacts your prediction error or whatever measure you care about when you've done that permutation. So clearly an important feature is if the values increase the model error. Because if I shuffle it and the model error goes way up, then it clearly was an important variable, and obviously it's unimportant if the model error was unchanged. So this idea comes from Bryman, really, but I think the most recent incarnation of this in the Fisher et al. Paper is really where it's kind of been generalized and sort of what we base our analysis on. So then the next one that I want to talk about, which isn't well known in statistics, or at least it hasn't been, it's called Lyme. And it's local interpretable model agnostic explanations. And so I think you'll see what I mean by this here as we go through it. So I'll kind of talk about the algorithm, and then these terms will become more important. The key here, though, is this local surrogate model. And a surrogate model would be like, well, we use surrogate models a lot in design of computer experiments, for example, where we have emulators, a black box model, and we emulate that, and then we learn from it. So that's been used quite a bit. This is a notion of building surrogate models to explain individual predictions. And it's the same idea, though. We just have some kind of explainable model that we fit to the black box model output, and that can allow us to explain what's going on. And so here's how it works. So you just select a prediction instance that the black box model made and that you would like to explain. You perturb the inputs for that instance, and then get black box predictions for these new perturbed inputs. So, we do that a bunch of times. And then you weight those according to their proximity to the instance of interest. And so clearly, if you would weight ones that were closer in the feature space than ones that were further away. And then you train this weighted interpretable model, say a regression model or a very short tree, for example. And you use that, you use the black box predictions as a response, and you use the perturbed data set as the inputs. And then, of course, you can explain what's going on because you have a explainable model that you interpretable model that you trained for the local model here. So here's just an example from the original Ribeiro paper, which is kind of cool. This is in the context of explaining, trying to classify this image. And you can see that when you try to figure out what it classified into, like, for example, there's a probability of 0.32 that was an electric guitar. This is why it thought that's what it was. This is why it thought it was an acoustic guitar, which was probability 0.24. And then this is why it thought it was a Labrador. So I think it's a cool example. Not all the examples work this well, that's for sure, but this is a good indication of what it's trying to do. And then the last one that I'll talk about, and it's the most, I guess, sound theoretically, are called Shapley Values. And it's a game theoretic approach to explain output from any machine learning model. And it's been around a long time, as I'll tell you in a second. And just hasn't been used that much in statistics. And I'm not really sure why, because I think it's once you start looking at it, it's really got some nice properties to it. And similar to Lime, the problem is we're going to distribute the prediction score of a model into these base features to try to help explain what's going on. So this was inspired by game theory by Lloyd Shapley back in the early 50s. And he actually won the Nobel Prize for this in economics in the area of cooperative game theory. So the idea is, so if you determine the values of players in a game individually and in all the possible subsets, and so we'll talk about this at some point, you have to have a value function that you can assign to these things. But once you do, then you can determine the marginal values for the players from all the possible orderings. And so you can see, you know, depending on which orders they are, then they may be playing the game differently, but there's still a value associated with that. And then the Shapley value is just taking the average of these marginal values. And so we can see that player A, for example, has more marginal value than player B does in this particular game. So more formally, if I had n players, and this is about as technical as this talk gets, by the way, the characteristic value function new here just maps these subsets, all the possible subsets, to some real value. And so what we really need here is we need to know what the marginal contribution of the player is, and that's given by this delta. And then this formula here is really, if you look down here, all it's really doing is it's just going to look at this marginal contribution that player I brings to the coalition, and then it's sort of dividing by the number of coalitions, excluding that player of the same size. And so it's a really cool way to think about it. You know, obviously the real challenge here, there's two challenges. One is being able to establish what this value function is. And the second is the sort of combinatorial part of this, right? If I've got a lot of players, then all the possible coalitions can get quite computationally demanding, if not impossible. So it's got some really nice properties. It's unique. It's got symmetry. It's got additivity. All these things are helpful in establishing, you know, that you can actually, given that particular value function, explain what you think you're explaining. And so in predictive modeling then, so how does this apply? Well, we think of the game now as a single outcome. So a single prediction instance, for example. So I have a bunch of X's and I want to predict Y. So the players then are the features. So I have P features here. And then I have a value function for the model F. And then the Shapley value for the ith feature is basically, it's just the influence of that feature on the outcome. And so the key here is how one defines this value function, as I mentioned. And if this talk were just about Shapley values, we could spend a lot of time on this, but instead I'll just refer you to one of the methods that I think is one of the more popular ones, called SHAP, which is conditional expectation variance. And it actually is kind of nice because it's related to this to Lime in a way as also, but I won't go into that. It's kind of beyond the scope here, but just keep in mind that there are plenty of ways to do this, to establish this value function. And the biggest problem with that is that it's going to be pretty computationally intensive. So there's a lot of different variants that help with specific computational concerns, and in some cases for specific models, so they're not so model agnostic. The key here, though, is that the Shapley value interpretation is the average contribution of this feature to the prediction. It's not the difference in the prediction when we would remove the feature from the model. Sometimes people think that. That's a different type of interpretability question. So this is more just the average contribution of that feature. If you thought about all the possible ways it could come into the model. Okay, so enough of the background. I want to talk about the example that we applied this to, and this was one of the challenges, honestly, was to come up with an example that we thought would be illustrative. But since a lot of examples in environmental statistics these days have sort of space and time in them, and that's kind of my interest, I kind of probably steered it this way. But we had interested in sort of long lead forecast of soil moisture in the Midwest US. This is the Corn Belt sometimes, because a lot of corn production, maize production happens here. And we're thinking about, well, what would happen in terms of the sort of Pacific sea surface temperature anomalies, which we know have a lot of impact through El Nino, La Nina, and also through other kinds of teleconnections. So how would those, like 3 months before and the lag soil moisture, impact our ability to predict soil moisture in the future? And that would be important because if you're a producer of corn, knowing what the soil moisture conditions would be 3 months ahead of time would potentially help you decide on your management practices. So we had data from 1948 to 2013 that we used for training, and then data from 14 to 21 to assess model performance. So this is just showing you a correlation between sort of on averaging across all the corn pixels for each pixel of the sea surface temperature anomalies, and you can see there's some significant correlation, positive and negative, over large swaths of the Pacific Ocean. And so suggests that there's probably some skill, and some previous work had shown there's long lead skill for some of this kind of prediction as well. So here's the models we consider. The first is sort of a baseline parametric model. We used spatial functional linear regression, and you can kind of see it here. The key to it is that it's got the lag soil moisture. It's also got a little seasonal term in it. But then the important part, I think, is this functional regression part, which is basically sort of averaging over the soil moisture, the sea surface temperature anomalies, and then there's a weight associated with that. So you could get then basically spatially varying regression coefficients through, these are basis functions here, which in this paper I think we're using empirical orthogonal functions, but you can then get the basis functions through this sum. So we used lag soil moisture and lag SSTA soil moisture anomalies, sea surface temperature anomalies as input. We also then used extreme gradient boosting, and in this case, we use clusters of the sea surface temperature anomalies based on empirical orthogonal functions and a meteoroid clustering algorithm. And that was just because it reduced the number of inputs to make it faster. We did deep artificial neural networks, and we had two versions of this. One that kind of used all the lag SSTA locations as inputs, and the other one used principal components from the EOF decomposition as inputs. And we had deep convolutional neural nets, and one model used just the sea surface temperature anomalies as input, and the other used that and the lag soil moisture. And then we compared these to reference predictions, climatology, which is just saying if I'm predicting May, then I'll just use the May average over all my training data for that prediction. And then persistence, which is saying if I'm predicting May, then I would just use, say, the value from February of that same year and say it's going to be the same. And those are both pretty traditional kinds of things that we try to improve on in meteorology and climatological forecasting. So this is showing you the results of the prediction, not the interpretability part, And up in this little tiny part up in the corner here is showing the functional linear model predictions, and the bluer it is, the better, for if we're predicting all months and then versus just the May months. And the May months are really the thing of interest here because that's the planting time, and that's really what the farmers and producers would be interested in. But we also considered all the months. So these are all the methods that I just talked about. And you can see for all months, only 3 of the models actually have skill beyond just the persistence forecast. And I'll talk more about that at the end. And then for the May months, only 2 models did. Really, the spatial functional linear model was the only one with significant skill. The XGBoost had some skill as well. So that was kind of disappointing, but again, I'll talk about that in a bit. Well, let's look at the interpretability part, just as a reminder of what El Nino and La Nina patterns look like. There are things in the Central Pacific, and then often they have other areas of the Pacific, tropical Pacific, showing significance, and then this kind of warm tongue that comes out and then kind of goes down to South America. So, so this is showing you first the results from the functional linear model, the permutation feature importance. You can see patterns that suggest that El Nino regions are important, but you also get some interesting things like you see across the other side of the basin, you have important areas, and then right along kind of the northwest coast of North America, you also see the importance. This is on the right, then, what the spatial regression coefficients from that model would show. Because remember, this is a parametric model, so we can actually, it's an interpretable model already. And you can see some of the same patterns show up, but not everything. Especially if you look in this region off the southeast or southwest part of the US, doesn't really show up in the permutation feature importance. And it's kind of interesting. Again, one could talk a lot about this kind of stuff, or the results here if we had more time. This is the XGBoost results, and XGBoost also has its own gain measure that can talk about feature importance. And then this is the Shapley value. This is averaging all of them for each instance. And you can see some similar structures show up as being important here, but there's also some things that are different. And then the really important thing about Shapley values is that they can show different important features for different prediction instances. So this is 2016, 2021. Some things are similar, but it's quite different. And so different regions of the sea surface temperature are important. It turns out that 2016 was a big El Nino year. And whether that's important or not, it probably is, but this would provide a mechanism for climate scientists to try to understand the difference between what's going on in 2021 versus 2016. This is interpretability results for the CNN, and the first one, the top one, is the Lyme result, and this is harder to see because of the pixelation here, but this is again for 2016, and you can see these regions that are redder than the others that are suggesting some importance. And then this is kind of interesting because this is from the Shapley value, and this is for 2016, but this was the model, the CNN model, that had soil moisture and the sea surface temperature anomalies. And you can see this kind of same El Nino region that we identified as probably important, as well as some of these other regions. But I think the telling thing here is that because these things are comparable, is that the soil moisture is actually more important as a predictor, at least for part of the region. And that doesn't surprise me because at only 3 months lag, 3 months previous soil moisture is going to be pretty important predictor. So that was kind of confirmatory in a sense. So a couple points here. One is that the spatial functional linear model and XGBoost were the only models that provide skillful forecasts of May. So why is that? Well, linear models have been shown to be reasonable models for long lead prediction of soil moisture in past. Nonlinear models can outperform them, but not uniformly. And so it's typically a function of the lead time. So at higher lead times, the nonlinear models typically work better. And it also depends on the subregion, because even though the Corn Belt looks kind of small, there's a lot of variation climatologically over that region in terms of weather in any given season. So sometimes the nonlinear predictions are going to be better in certain parts of that region, and some parts of it, the linear models will. So I think in some cases here, since we're kind of averaging over all of the prediction space in terms of the soil moisture, I think that it kind of averages out some of the importance that might be seen by, say, XGBoost, for example. Lag soil moisture is important, and this is, again, not surprising, because particularly for May, because there's probably not that much of a difference, but most of the soil moisture in February comes from the melted snowpack, and that's probably still going to be there. It has typically not warm enough in that 3 months to evaporate that. So it's probably going to be a pretty good predictor. And then why didn't the deep models work well? And I think it's pretty clear that there's probably not enough data here to adequately train these. If you think about it, there's only 66 May values in the training set, and that's kind of a crazy small number for training deep models. And also, none of us were really consider ourselves experts on these models, and we didn't spend that much time trying to tune the architectures to this particular problem either. Last slide here is talking some about just the explainability part, which is what we were trying to do here. There were definitely consistent, if you looked at all the plots, and I didn't show all of them, there's definitely consistency in terms of which regions of the SST are important for various models and metrics, but not 100% agreement. And I think that is very much why one should look at multiple explainability metrics when they're trying to understand models, because they each have different things they focus on. And the other thing is that is present here, clearly, because we have spatial images as effectively predictors. There's a lot of dependence, and most of these methods have some issue when there's a large amount of dependence in the predictors, and in various ways. And so I think that's always the case, even with interpretable models like linear regression. Obviously, if you have a lot of collinearity, it clouds your ability to do interpretation. And so there's no magic bullet here. These all suffer from that to some extent as well. The other thing is that these things can be very computationally expensive, particularly Shapley and Shapley values, when there's a lot of input features and multivariate responses. So we really gave this one of the most difficult problems that we could, and I think it showed. And it limits our ability to consider other alternatives and different tunings. And then one of the things here is one of the real strengths of these local interpretable model agnostic metrics is their ability to explain individual instances. But it can be quite labor intensive to go through those and try to summarize them. So a lot of human interpretation has to then go into it. And as we learn, that just takes a long time. And so it's nice to have ones that are global, and they only have to look at one map, for example, but you lose some of the value of doing these things in the first place. So that's all I had for you. And the paper that this is all based on is listed at the bottom here. Molnar's book, which is awesome, is online. You can find that easily. And then some of these other things that were referenced in the paper. But if you have any questions at all, feel free to shoot me an email at this address, and I'm happy to chat with you or provide any references that you might need. Thank you.
Thank you so much, Chris, for this amazing talk about artificial intelligence in environmental statistics. I will